This instructional video is designed to show you how to apply the van der Waals equation in comparing the behavior of a gas against real versus ideal conditions. In this case, we have to have the identity of the gas and its van der Waals A and B constants, as well as the number of moles, temperature, and volume, because we're being asked to compare pressures. So for the ideal pressure, we have P equals nRT over V, and I'll be suppressing the constants just for ease and speed of writing. So we have our 15 moles of chlorine, we have our ideal gas constant, and we have the temperature, which this time is already given in Kelvin. We're going to divide that by the volume, which is 3 liters. So ideally, the pressure we should find is 307.7 atmospheres. Now, in order to do the comparison, we'll need to solve the van der Waals equation to express everything in terms of pressure. And that's relatively straightforward algebra to do. We have P equals nRT over our volume term, V minus NB, and we subtract off our interaction term, AN squared over V squared. And so now we can substitute in all of our values and determine a quantity for the pressure under real gas conditions. So again, we have our 15 moles, 0.08206, our temperature in Kelvin, and we're going to divide by the volume, which is 3 liters, minus the number of moles, times our van der Waals B constant, 0.0562. And now we subtract off the interaction term, our van der Waals A, 6.49, number of moles is 15, we have to square that, and our volume of 3 liters will also be squared. So this takes a little more effort to step through everything. However, in the end, what we find is that our first term gives us 428 atmospheres. Our second term requires us to subtract off 162.25 atmospheres. And this gives us a pressure of 265.75 atmospheres. And this is under the van der Waals equation. And so we can see that there is a significant deviation from real gas behavior to ideal gas behavior, because we do not account for the fact that gas particles take up volume and interact with each other when we're using the ideal gas law.